Hi guys, this is the second question from the moving coil, moving charge and electromagnetism. So coming to this one, this question regarding to the moving coil galvanometer. Okay, so now here a moving coil galvanometer has 100 turns, and each turn has area of 2 centimeters square, right? The magnetic field produced by the magnet is 0.1 Tesla. That means there will be a magnetic field like this, and between these two magnetic fields there will be a moving coil galvanometer. So moving coil galvanometer has a coil. This coil has 100 turns, right? For this coil, there will be a needle attached. A needle will be attached to this coil. When you send current to this coil, then what happens? Magnetic field will be produced here. This magnetic field will attract and repulse with the external magnetic field. So due to the repulsion, the coil takes turn. Okay, when the coil takes turn, this wire will twist because torque force will be created on this coil. If you see the top view of this coil, this is the top view. If it is A, it is B, then this is the top view of the coil. Then forces will be like this. Due to this forces, it takes turn, right? So the coil takes turn. Due to this turn, the needle which is attached to this twisting wire also gets turned, and it shows the reading of the current. If you send more amount of current, the twisting will be more. If you send less amount of current, the twisting will be less. So here what they are saying, the external magnetic field strength is B is equals to, first of all, number of turns. N is equals to 100 given data, and area is equals to how much it is, 2 centimeters square, 2 into let's convert into meters, 10 to the power of minus 2 meters square. So 2 into 10 to the power of minus 4 meters square area, and amount of current produced by magnetic field is B is equals to 0.01 Tesla, and uh, the coil is 0.05 radians. They have sent some amount of current. See, deflection, the coil is 0.05 radians when the current of 10 amperes. So current I is equals to 10 milliamperes. Do remember that milli in the sense 10 to the power of minus 3, right? So 10 into 10 to the power of minus 3 amperes current, and deflection is 0.05. That means theta is equals to 0.05 and radians, 0.05 radians. And then when the current of pass through it, the torsional constant of the suspension wire, torsional constant they are asking. The torque force, when it rotates, the wire which is attached to this coil gets twisted, right? So again, due to that twisting force, we can call it as a torque force, restoring torque. When it is twisted, then due to this restoring torque force, the coil want to come back. That means the applied force will be equal to the restoring torque. So restoring torque is equals to, the force will be BANI sin pi. You know this very well, right? The force on the coil, right? When you keep it in magnetic field, BANI sin pi. So do you remember what is tau here? Restoring torque force, right? You take any wire and rotate it. Again, what will happen if you leave it? It tries to come back. So why it is coming back again? Because of restoring torque force. So this restoring torque force will be equal to BANI sin theta. B in the sense external magnetic field, amount of area, N in the sense the number of turns, I in the sense the amount of current passing in the conductor. If you send more amount of current, then the twisting will be more. Automatically the torque force also, restoring torque force also will be more. Here the restoring torque force will be directly proportional to theta. Okay, now restoring torque force will be directly proportional to theta. If it turns more, then what happens? the restoring force will be more. If you take as a rubber, if you get it stretched, then as you stretch more, it tries to come back that much of force. Stretching force will be more, right? Restoring force will be more. Same. If you twist it more, the restoring force also will be more. So now from tau is equals to some constant into theta. This constant is called nothing but torsional constant of the excuse me, torsional constant of the suspension of wire. It tells the torsional constant. That means C is equals to tau by theta. Per unit thrust, how much torque force will be there, right? So this C value they are asking to find out. So now instead of this tau, we excuse me, instead of this tau, we apply C theta. C theta is equals to BAN I sin pi. So here the flux will be changed always perpendicular, right? So now sin pi means you can take it as 90. So C is equals to BANI by theta into sin 90. Sin excuse me, sorry, right? Sin 90 value 1. Now C is equals to B value is 0.01 into what is area? 2 into 10 to the power of minus 4, 100. I value is 10 into 10 to the power of minus 3 by how much theta it is? 0.05. Let's solve this. Here if you multiply this 100 with 0.01, it becomes 1, cancel, right? And here 10 4 3 7, and 7 minus 1 means 6. So 2 into 10 to the power minus 6, right? Now 2 into 10 to the power minus 6 and then 0.05 by 0.05. If you divide with 100 by 100, then what happens? It's like 2 into 10 to the power of minus 4 by 5, right? Now further, if you solve this, let me try to solve here. I think it is visible. Let you take 20 into 10 to the power of minus 5 by 5 in this 4 times. So the answer is C is equals to nothing but 4 into 10 to the power of minus 5. What is the x value? X is equals to 4, right? I hope you understand well. So you should remember this formula and this concept also. This is very important, right? Tau is equals to BAN I sin pi and pi will be 90. Here tau is restoring torque, right? The restoring torque is directly proportional to theta. This is how you have to calculate. Thank you.